We've already built the oscillator, video basics, borders, ball counters, and ball motion controls on sheet 1, the paddle logic on sheet 2, and the flip screen circuit on sheet 4. Today we're back on sheet 1 to hit the bricks. Once again, we're going to use the RevFX schematics because the RevF schematics in the manual do not exactly match the RevF boards. See Part 2 or the differences document in GitHub for details. First, we'll need to tear out our old fake brick wall and cheap break hit signal generator. Then we'll need the 82S16 256x1 bipolar RAM chip in LUB3, and yes, that's 256 bits. We'll need a new 7474s in EZ6 and Dog3, a new 7410 in Mary 4, a new 74279 in Fox 7, and a new 7411 in Fox 2. We'll also use a wide variety of existing gates from Charlie 2, Henry 4, Henry 3, EZ1, King 4, EZ5, EZ3, and Dog 2. This is a smaller section of the schematic, but there's a lot of nets to wire up here. I think over 50. To save some time, I'll just use jumpers for now and hardwire this afterwards. For a quick overview, each brick is stored as a bit in the RAM using visual screen placement as the address. Bricks only show up if the bit corresponding to its screen address is on. At the beginning of a game, the RAM is filled with all ones. During play, when a brick is hit, its bit is set to 0. Let's just start with these enable signals, which tell us where the bricks will sit visually. Naturally, we'll map it out, and you're getting pretty good at this. All of these enable lines must be low, so 32 Henry and 128 Henry are easy and must be off. For the third enable, both inputs to this NAND gate must be high, so VSync and 64 Henry must also be high, and the basic block of bricks will sit here. These three vertical lines provide brick column spacing, and when I say column and row here, it's from the player's perspective. The easiest way to look at this is that only when all of these are on, the output goes low, blocking this enable. This happens in 16 places, but we can eliminate these two because they're already blocked by VSync. Now that we have our 14 columns of bricks, how do we get the rows? This is done after the brick data leaves the RAM chip. Once again, when both of these signals are high, they suppress data out from reaching brick display, giving a visual gap. This is the only place 1 Henry is used in the design. Note that the ball cannot hit the vertical gaps since they're part of the enable logic, but the ball can hit the horizontal gaps because they are only visually suppressed and do not affect the hit detection flow. From the video lines, you can see that there are 8 rows and 16 columns, and we can go through and assign a bit address to each brick according to these signals. The mapping really doesn't matter. We can switch all these lines around and the result is the same. 1 memory cell represents each brick. The only thing to note here is that there are 2 brick arrays stored in RAM, 1 for each player, and that there are also 16 unused cells for each player. Let's map out a few brick RAM addresses for fun anyway. For address 0, all these lines are off, so that brick sits here. The first 3 address lines are mapped to horizontal signals, so addresses 0 through 7 are all in this column. They didn't map these next 4 signals in weighted order, so the pattern gets a little strange. The next address line is 32 Victor, so the next cell sits here, and the sequence progresses through all rows in this column. This pattern continues skipping columns. Then we go back and fill in the gaps when 16 Victor finally rises. The last column represented in memory is outside the visual area, and we also have this column at the bottom. Well, we just did all that work, but That was actually the mapping for player 2. When player 1 is up, this last address line is high, and that mapping is exactly the same, except it starts at hex 80. I temporarily took that RAM chip back out, too afraid I screwed something up. Pricey little bastions. Before we put that chip in, let's test out some of the logic by shoving those enable lines through a 3-input OR gate and connect the output to simulate that data outline as if bricks were all there. This should show us what the real brick array will look like. Since the 7400 series doesn't have a 3-input OR, we'll make up our own. In De Morgan notation, this would be a negative 3-input NAND, because you want the output to go low only when A, B, and C are low. Power that up. No smoke. Always a good sign. That looks pretty cool. You'll notice that this column of bricks sits just inside the left boundary, but they're not brighter because the bricks and boundaries are merged in logic. In part 5, I mentioned that there's an interesting artifact of the unbalanced clock line where 1 Henry and 2 Henry transitions are asymmetrical. This happens where the clock line has a double pulse. This anomaly finally becomes symmetrical starting with the 4 Henry counter stage. You can go back to part 5 to see how this strange clock is generated. We just showed how 1 Henry and 2 Henry create the visual row gaps when both are on, and you can see this signal in the waveform here. The video counters have random values at power on, so the combination of 1 Henry and 2 Henry can start in 4 different states. I'll leave the clock waveform alone for reference and go through the rest. If both lines are low at this point, the counters make these transitions, and the combination of 1 Henry and 2 Henry is 4 clocks wide. The next 2 scenarios have the same result, 4 clocks wide. But in the last scenario, the combination is only 2 clocks wide. Whichever scenario occurs at startup stays like this until you power it off. Since this is used for the row gap, approximately 25% of the time after power on you'll get slightly fatter looking bricks because the row gaps are narrower. You can see the difference between these 2 screenshots. It's a minor thing, but I noticed this strange behavior and had to figure it out. Sorry. We only have 3 additional lines to work on: data in, data out, and read-write. All pretty much self-explanatory. To write a bit, you set the target address, place the desired bit state on data in, enable a chip, and drop the read-write pin. To read a bit, you just need to give an address and enable a chip. The state of the read-write pin has no bearing for read operations, and the datasheet properly calls this write enable. The data outline is inverse of data in. Kind of strange design, but for the output they have open collector versions that can be tied together in an array. Open collector outputs only drive low, so they must be pulled high. Hence our addition of the optional R61 on the schematic. You see many boards with 1K resistors soldered above the chip. I'm assuming they sometimes use open collector parts to expand their sourcing options. Data in goes high when either of these 2 lines are high or either of these 2 lines are low. Write enable goes low when any of these 3 lines drops. These FPD lines come from the scoring logic, which we haven't built yet, so we'll just tie these down and tie these up for now. These lines are used to populate a player's second wall of bricks. Not sure what FPD stands for? Full player data, forced player data? Well, let me know what you think. Anyway, it's probably easier to look at the remaining circuitry as 2 distinct functions: putting up a full wall and clearing individual bricks. We'll start by building a wall first, which is handled by this set bricks flip latch. Start game 1 drops when you press either of the game start buttons. This sets the latch, turning on set bricks and raising data in. To store those 1s, we also need to drop the right enable line, but all we have here is this brick hit line. To force brick hit low, they force set this brick hit latch and disable resetting the latch here. At this point, brick cells are set to 1 as RAM addresses are continuously scanned. This writing style is unusual, but once again it works. Here, write enable is held low and the chip enables do the writing. Also to note is that the addresses and chip enable lines change nearly at the same time. The saving grace here is that 64 Henry goes through 2 gates, delaying CE3 a tad. Anyway, this setting to 1's cycle continues over and over until the serve button is pressed in release. This raises serve wait and turns off the latch. After that, set bricks stays off and data in goes low until you start the next game. Now I know what you're thinking right now. No, not that you don't have a life. I already know that because you're watching this. You remember that we have RAM cells for 2 sets of bricks, and what we described is only for 1 set. We need to take a peek at sheet 2 where this player 1 RAM line is generated. Here, player 2 is low after pressing one of the start game buttons, and when set bricks is low, 2 Henry is gated to the player 1 RAM signal going into pin 11. Able 7 is therefore included in the set bricks address roll, and cells for both players are set to 1. We don't have this logic in place yet, so we'll just tie pin 11 down for now and use only 1 array. In a similar fashion, those FPD lines are asserted when a player completes their first wall, refilling their bricks by raising data in and dropping write enable. This cycles through all of that player's addresses, setting their bricks. Set cycles continue until the ball hits the paddle and deasserts those lines. Well, we finally get to clear some bricks. Note that data in is simply held low during gameplay, so any write operations will turn off bricks. This logic here has a tiny bit of similarity to our cheap brick hit stuff. They reset this SR latch when a brick is hit, and set the latch when either the paddle or top boundary is hit. This gates the ball display signal only when the SR latch is set. If RAM data out is low, where a ball appears, it raises the brick hit latch data line, turning on the latch when the check ball hit clock rises. This brings up the brick hit signal and drops the write line, storing a 0 in that brick address. The latch is reset on the rise of the check clock if there's no brick or ball. Note that they use the ball hit clock here instead of the clock line because CKBH rises in the center of each clock. This offset assures that everything has settled before checking for a hit, and delays the write line drop to assure adherence to the timing cycle parameters. Since the latch is reset on the next rise of CKBH, write enable rises before any other RAM line changes. This assures that only the proper cell is modified. Like usual, I need to shut up and turn this on. We'll need to hook brick hit into our X motion controls as well. I'm going to just leave attract mode on for now and let's see what happens. Wow, I forgot that RAM cells initialize randomly, and it looks like the hit logic is working. Very cool. Hit the Start One Player Game button. All bricks appear. And ball goes right through because we don't have the game state logic to suppress it. And the set bricks latch is still on. Press serve. Well, it looks like it's all working. Easy mode. I can watch that all day. Let's wait until at least one high value brick in the back 4 rows is hit to check the speed up logic we built the last time. Yep, SU rises, making both axes fast. Reset that. Turn off attract mode. And start. As always, a final quick test for flip screen. This is using the same brick array for now, but working nominally. On to the boring part. We'll make our own 82S16 symbol. Drop in all the required gates. Rename everything. And wire it up. I'll try to clean this up a bit before the next video. Looks like a winner. That's enough for today. At this point, we really need that game state logic, so we'll button that up in the next video. Thanks for watching.